In the previous lesson, we saw what we mean when we say a function is continuous at a point, or that a function is discontinuous at some point A. In this lesson, we are going to talk about the types of discontinuities at a point. Our essential question is that how can we determine the types of discontinuities? So you answer that question. Okay, let's recall the idea of continuity that we talked about in the previous lesson. We saw that a function is continuous at the point x equal a if three conditions are met. The first condition was that f of a is defined, that is, the function exists at the point a, f of a is defined. The second condition is that the limit as x approaches a of f of a exists, or in other words, the left-hand limit equal the right-hand limit. This function meets condition 1 and condition 2. The limit as x approaches a of f of x exists. And our third condition is that the limit as x approaches a of f of x is equal to f of a. But this function does not meet that condition because the limit as x approaches a of f of x in this case is different from f of a. So it doesn't meet that condition. This function, however, meets condition 3. So this function meets condition 1, 2, and 3. So this function is continuous at the point A. Let us look at some examples to introduce the topic of today. Where are each of these functions discontinuous? At what point is each of them discontinuous? The first function, remember we have talked about this. This function, you can simplify it as x minus 2 times x plus 1 divided by x minus 2. And this will cancel out with this to give us x plus 1. But the difference between this and this is that this one has a hole at the point x equal to. At the point x equal to, this function is not defined. For the second function, x cannot be equal to 0 for this part. So we redefine it at the point x equals 0. We give it a value of 1. And the third one is the same, but we have redefined the function at the point x equal 2. So c is the same as a, but we redefine the function at the point x equal 2 to be 1. Example D. This function is an interesting function in calculus. It is called the greatest integer function. And it is defined by the largest integer that is less than or equal to x. So if you are at the point 3, the largest integer that is less than or equal to 3 is 3. 4.7. Greatest integer of 4.7 is the largest integer that is less than or equal to 4.7, which is 4. And 9.9 is the largest that is equal to, greater than or equal to, less than or equal to 9.9, which is 9. So we are asked, where is the function discontinuous? At what point is the function discontinuous? Draw the graphs of each of those functions that we have just talked about. Of these functions, remember there is a hole at the point 2 here for A, and that is the graph of B. It is defined at x equals 0 to be this, and C is defined at x equals 2 to be 1, and here is the greatest integer function that we just talked about. Okay. The graph, in each case, the graph can't be drawn without lifting up the hand. If we look at each of these cases, you cannot draw the graph without lifting up the pen. This means that the functions are discontinuous at some points in their domain, because there is a hole, a break, or a jump on the graph of the function. The kind of discontinuity in A and C is called a removable discontinuity. Why? Because we can remove the discontinuity by redefining f at just the single point. Let us go back to this graph. If for A and C, if we come here and we redefine the function, remember this function is the same as x plus 1, but it doesn't exist at the point 2. But if we redefine the function by saying it is equal to 3 when x is equal to 2, then this function will exist at this point, right? Equally, we can come here and instead of saying it is 1 when x is 2, we say it is 3 when x is 2. Then the function, this comes up to here. And when it comes up there for each of these cases, the discontinuity will not exist any longer. So we have removed the discontinuity. So this kind of discontinuity is called a removable discontinuity. The discontinuity in the second part is called infinite discontinuity. Let's go back and look at it. In this part, you realize that this function is going to infinity. It is discontinuous because it is going to infinity. In other words, this line is a vertical asymptote. And because of that, we call it an infinite discontinuity. And the discontinuity in this third part is called a jump discontinuity. For this one, it is called a jump discontinuity. This is jump discontinuity. Why? Because you can see that for each of these points, the graph jumps to another part. The graph reaches here and jumps to another value. So it is a jump discontinuity because the graph jumps at each of those discontinuities. Okay, that is it about types of discontinuities. Please download the worksheet and solve all the exercises. Thank you.